Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on current source inverter, that is CSI. So in that R load, C load, capacitive load, resistive load and parallel resistive and capacitive load. So first here, what do you mean by here there are different types of inverters: voltage source inverter and current source inverter. In the voltage source inverter, we have already discussed a single phase bridge inverter with RLC load, and in the full bridge inverter also RLC load. And also we have in the voltage source inverter category, so 3-phase 180 degrees conduction mode and next 120 degrees conduction mode inverters we have discussed. So now today we are going to discuss current source inverter, that is CSI with R load, C load and RC load, parallel RC load. So here what is a voltage source inverter and what is the current source inverter? So first I will define. So first, the current source inverter is a type of inverter that changes DC current at its input terminals and equivalent AC at output terminal. So now here in case of voltage source inverter, so a DC voltage is converted into the AC voltage, but here DC current is converted into the AC current. So now here this is the current source inverter diagram. So single phase current source inverter circuit diagram. So now here T1, T3, T2 and T4, and now here there is a load is connected between these two terminals. So here is a current source. So in the previous case, in the voltage source inverter, we have voltage source, but here, so why we am attaching here current source in parallel with inductor. So here we know the inductor property. Inductor does not allow sudden changes in currents. So here voltage source in series with the inductor indicates the current source. Here there is no current source is available in the market. So first here we have the current voltage source in the market, we have the inductor. So from this series combination of voltage source and inductor, so we can make the current source. So that we can make the current source inverter circuit diagram. So now here current source in series with the voltage source in series with the inductor. So that is the current source. Here this is the current source. So now here I will explain. First I will explain R load, C load and parallel RC load. Parallel RC load. So first this is the circuit diagram for current source. So here this is the current source. This is entire circuit is known as a current source in parallel with inductor in parallel with. This is a voltage source and this is a V input and this is the inductor L. And now here we have switches S1, S2, S3 and S4. This is the output voltage and this is the output current. So now this is the source current, that is the IS. So now how it will work, how it will operates first. So first when S1, S2 will conduct, so 0 to T by 2. So here 0 to T by 2. So what will happen? And next T by 2 to T, what will happen from 0 to T by 2. So what will happen first, this IS current. So this IS current will flow from S1 through the load and through the S2 and come back to this one. So this is the when 0 to T by 2, S1 and S2 SCRs will conduct the current direction. It looks like this. This is the current direction. Sorry. This is the current direction. And next here from T/2 to T. So let me change the color over here. So this is the let take this color. So now here 0 to T/2. Here I am taking green color. So now here, so from 0 to T/2 to T. So here this is a S. So here in this way, see the green color. So now here current direction is, it looks like this. So now here from this we can conclude that from 0 to T/2 the current is source current is in the direction of IS, but here T/2 to T, so S3 and S4 will conduct. In that case I0 and IS is in opposite direction. This is in the direction, this I0 is in this direction. So now if you see this diagram, so I0 is positive, means here I0 equals to IS, that is positive. And next here I0 is negative, means I0 equals to minus IS. IS will not be never be negative, because it is a unidirectional current, not bidirectional. So here one more important point in the current source inverter, so it does not require any feedback diode. In case of voltage source inverter, so there is a feedback diodes. There sometimes the power may flow from load to the source, and sometimes may flow from load to the source depending upon the load. But here in case of for all loads, there is no direction current flowing from load to the source, but because of that reason current source does not require any feedback diodes. So now here this output voltage equals to I0 into this resistance R, that equals V0 into IR. So now here V0 is negative. So here during positive 0 to T/2, so output voltage is positive, and 0 T/2 to T output voltage is negative. So now here if you draw the graph for this current source inverter for pure resistive load for I0, V0 and Vin. Now here, so this is the T. So for these I am dividing this time period T. So this is off time period 0 to T/2. So the which thyristors will conduct? So T1 and T2, S1 and S2 thyristors will conduct. So 0 to T/2, here S1 and S2 thyristors switches will conduct. And next here from T/2 to T, S3 and S4 switches will conduct. So why it is positive, why it is negative? Here I0 equals to IS. So this is equals to IS. So plus IS. So IS in the direction of I0. But in case of S3 and S4, so here IS direction is opposite to the minus I0. So minus IS, this one. So IS is never be negative, but here that signs are different. Now here, so it is a voltage stiff type of load. For in case of R load, current source, current value and voltage value both are in phase. Vectors are in phase. So current, it will follow output voltage, and output voltage follows the input current. This one is also same. So this is the output voltage, V0 equals to I0 into R. And now this and next this one is also same, I0 into R, but it is a negative. S1, S2 switches will conduct. Now here what about this input voltage? So now if you apply KVL in this loop, so if you apply KVL in this loop, what will happen? Let me change the color over here. So let us take this color here. Now if you apply KVL in this loop, first loop, this in this loop here. So now here what will happen? So minus, so here V naught equals to V in equals to minus plus, and this one, so minus plus. So now here minus plus, and this one is a plus minus, I think. So this is plus minus, and Vn equals to plus minus, and next here minus Vin, and next plus V naught, that equals to 0. V naught equals to Vin. So here it will be like this here. And next in the second loop here, so from this here to here, so this is minus and this is plus. So now minus V in and minus V naught, that equals to 0. So V naught equals to minus V in. So now this is a minus V naught and this one is a V naught. So now here it is a here up to here this one, and this is the negative of this one. So V in equals to minus of V naught. So here is not negative, it is a positive. So the diagram will be, it looks like this, both are, it will maintain the constant voltage. V input is always positive in case of current source inverter, in case of R load. Now here what are the formulas related to this current source inverter? This is a IS. And now here RMS output current, this is the output current. So now if you calculate this output current for current source inverter CSI, so now here RMS value of output voltage of this current source inverter for this resistive load. So now if you do the calculations for this is maximum value is IS. So now if you do this one, here this is the square waveform. If you calculate the RMS value, you will get the IS value. Now here for this one is also RMS value equals to this I naught RMS value into R. You can calculate this V naught RM, V naught VS, V naught V input is also. So that is V naught RMS. So now square this waveform and take the average and take under root. So that is the RMS value, and you can take the average and RMS values of thyristor currents. So here this is the output currents. So these are the output currents. So now here what about the thyristor currents? Thyristor currents means here S1 and S3 thyristor, S2 thyristor silicon, S3 and S4 thyristor silicon. So that switch currents average value. So average value and RMS value. So that is the, so here that this waveform average value is IS by 2, and if you calculate for this one, so that is the I naught IS by under root. And now here Fourier series expression for output current and output voltage. So now we know very well this formula for a full bridge inverter, voltage source full bridge inverter. So that equals sigma n equals 135 up to infinity 4 Vs by n pi sin n omega naught t. We have already discussed in case of that is V naught equals to t. But here there is a I naught IS. So that is IS, and this is the I naught of t. So this is the square waveform. So if you make this in the form of Fourier series of output current and output voltage is also same. This output voltage equals to IS equals to V naught equals to V naught of as Vs equals to now IS into R. So now here sigma n equals to 135 infinity 4 into IS by R n pi sin omega naught t. So these are important formulas. So now here RMS value of output current, output to RMS voltage, and thyristor average current IS by 2, and thyristor RMS current is IS by root 2. This is the Fourier series equation for current and voltage. So now here next formula, fundamental component of RMS output current. So you can calculate this one. So here from this one by root 2 here. So here if you do this one 4 into IS by n pi. Here fundamental means n equals to 1, and now here, so by root 2. By root 2 means here that is the RMS value of fundamental. Fundamental means n equals to 1. Sigma n equals to 135 infinity 4 into is by n pi sine n omega t. So now here if you put n equals to 1, so that is fundamental, and by root 2 means here, so that is RMS. So now here 4 root 2 by root 2 means 2 root 2 by pi. So here that equals to fundamental means 0 1 RMS, that equals to 2 root 2 by pi into is. That is fundamental component of RMS output current. So now distortion factor, we know very well about this one. So that is this fundamental component of V01 RMS divided by, so now output current, so that is V0 of output current, that is is. So now here, so if you do that one, that is distortion factor G equals to 2 root 2 by pi. So now total harmonic distortion, that equals to 1 by G square minus 1. This we have already discussed, that is 48.43. So now this is the case for RL load, and now here I am discussing about the C load, capacitive load, how it will works in the capacitive load. So now first, and another formula here, fundamental component of average and output current, so that is sine wave thyristor current. So now this one, so half wave rectifier, and now for this case here average S1 and S3. So now for this case average value, so I01 max divided by I01, this is I01 maximum value divided by pi, and maximum value divided by 2, and power across the load is expressed, so that is a V01 into I01 RMS into cos phi. So that is the power across the load. Next, total power means only not this fundamental. So here fundamental means you need to put 01. So we know very well about this formulas, and total power means no need to take fundamental. So now here I0 RMS square into R is equals to V0 RMS square into R. So now here voltage input is always positive. So because power is always flows from source to the load, not from the load to the source, it does not require any feedback diodes. And now here C load, so capacitive load. So difference I will tell you. So only the difference is here output current waveform is same, but here voltage waveform is different for different loads. In case of voltage source inverter is also output voltage is same, depending upon the load current waveform is changes. So for R load is different current waveform, L load is different, RL load is different. But here if you see the diagram, same procedure, same operation during the positive 0 to T by 2 duration. So S1 S2 will conduct, so current direction is like this. So this is a IS current, and IS equals to I0 current direction, same IS direction, this one. And next, if you change the color over here, so now here this is a next T by 2 to T. So same operation like in the R load. So this one. So here current direction, this IS direction is opposite to the I0 direction. So this is plus and this is minus. And now here 0 to T by 2 I0 is positive, I0 equals to IS. And now here V0 equals not IR. So now here in the capacitive load V equals to V equals to integral of 1 by C integral of I dt. So now here if you integrate it, first if you see the waveform for C load. So now here this already we discussed. So this is the I naught is same for all loads, all and now here this is the I naught. I naught is same, but this current is. So for any square waveform, if you integrate it, you will get the current triangular waveform. So here you will get the triangular waveform. This one. This is one. This is the waveform for this one. So now here this is a V naught maximum and minus V naught maximum, and now here this is the T by 4, T by 2, T by 4, and now here if it is 360, so this is a pi, 2 pi, pi by 2 and 2 pi by 2. So now here let me tell you first one here. In case of pure capacitive load, current leads voltage by pi by 2, and voltage lags current by pi by 2. So here it is the current waveform and it is the voltage waveform. So voltage waveforms lags current to voltage by, it starts from 0 and it lags voltage by pi by 2. And now here any square waveform, this is the current waveform and this is the voltage. Any square waveform, if you integrate it, you will get the triangular waveform. And next thing here, V input equals to V input equals to V naught. In case of 0 to pi by 2, V input equals to V naught, and V input equals to minus V naught. Already we have discussed. So my V input in case 0 to T by 2, it's S1, S2 will conduct, and next here S3 and S4 will conduct. S3 and S4 will conduct in the negative half cycle, and in this T by 2 to T. And now here this current is positive, same direction, and this current is opposite to the source current direction. So now here this V input equals minus V naught. So minus V naught, V in, this is a V in, and next plus V in, V naught equals to 0. So V naught equals to V input. So this is for 0 to T by 2. And next T by 2 to T minus V in plus minus V naught equals to 0. So that equals V naught equals V in from T by 2 to T. So now here, so this is the positive same V naught, V in equals to V naught, same as it is here. But here this is the different here. So this one is the waveform is different. So now this one is opposite to this one. How we will write opposite to this one means here this is the, sorry. So this is like this. Your output waveform, it looks like input waveform. So see, observe the input voltage, output voltage and input voltage. So now here this V input equals to V naught. Here V input equals to minus V naught. So observe this one. So it should be like this, but here because of this equation it is minus V naught. Okay. So now here there is a frequency changes. So now here this is a T, V output voltage frequency T time period is T, but here this time period is T by 2. So now here, so T not equals to T only, and T in equals to T by 2. So now here this is T by 2. So now here F naught equals to 1 by F and F naught equals to 1 by 2F. So there is a change in frequency. So now here if you see this waveform, there is a relation input frequency and output frequency. You can find out easily. So F naught equals to Fin equals to 1 by F naught. Sorry. So 1 by 2 F naught by 2. So that is the case. So now same equations. So this is the output voltage waveform. Sorry, like it should be here and here. These are the equations. This one. So now here average output, same equations. So output current is same for all loads, R load, C load, or parallel RC load. So that we have already discussed thyristor RMS RMS and average current IS by 2, that is IS S1 and S2 and S3 and S4. So IS by 2 and ITRMS equals to IS by under root. So now we know the formula. So this is same equation for current equation. Sigma n equals 135 infinity 4 into IS by n pi sin n omega naught t. But it is a capacitive load. So current leads voltage by 90 degrees. So this is the case. Omega n into omega naught t minus n pi by t. So and there is a capacitive load. So now here 1 by n into omega naught into C. So V naught. So fundamental dissipation factor. So that with C is 0. Dissipation factor means that is pi by 2 here. So that value is 0. And next here that cos pi by 2 is 0 means here everything is 0. So here V01 RMS and I01 RMS cos phi. So this is pi by 2 means 0. So fundamental component of output power is almost 0. Fundamental component average and RMS current, thyristor current is, so that is here. So this is the IT average. So maximum value by, so this I01 maximum by pi. So that is case. And next, so this I01 maximum by 2. And next here maximum output voltage equals to, how we will calculate maximum output voltage? This one maximum output voltage equals to IS by, this IS by 4FC. So this you can from the integration you will get. And next RMS value of input voltage is here V01 maximum by root 3. Next, parallel capacitive load. How you will get the parallel RC load? Here same scenario, output current is fixed for all load, for R load, C load or parallel RC load. Here the combination of parallel R and C combination. This is the load I am connecting here. This is the load I am connecting here. So here this is the current source and here this is the current source I am connecting. So this is the IS, same current is flowing, S1 and S3 switches we are connecting. So IS1 is equal in the direction of I0 direction. So now here S1, S2, here IS equals to I0 is always positive, this one. And next, during the negative off cycle, so not negative off cycle, S3 and S4 will conduct. So here this current is direction is opposite to this IS minus IS. So now here S1 and S3, S2 and S3 and S4 switches will conduct. And now here for capacitive parallel RC capacitive load, so here this is depending upon the load only, voltage will changes. So now here this voltage is the exponential. This voltage is a exponential. So here current leads voltage by, some phi angle, so that is a phi, and voltage lags current by some phi angle. So this is the pi, and this is the, so here 0 to pi, S1, S2 switches will conduct, S1, S2 switches will conduct, and S3 and S4 switches will conduct, and S3 and S4 switches will conduct. So this is the case. So now here is also same. So this is the case for current source inverter. So now these are the formulas. Now what are the advantages of current source inverter? Current source inverter offers easy operation as the circuit working is controlled by current source. That is, combination of current is limited voltage source serially by connected to the large inductance. So the circuit is designed in such a way that it can handle large voltage spikes at the time of commutation. And next, the four quadrant operation can be achieved without the need of extra power usage. And next, here unstable performance is noticed at light load, and next high frequency operation, and the commutation of thyristor in the circuit shows dependency on the load, which limits the operational frequency. And next, these are the applications. So first application is, it is used for speed control of motors and induction heating, uninterrupted power supply units, that is UPS, and plasma generator and switching devices, synchronous motor starting, and next here lagging VAR compensation, voltage ampere reactive compensation. I hope all these concepts are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.